All right, guys, so 9A and 9B, we're going to combine these into one video. And I'm going to try, I'm going to try not to ramble. I'm going to try to really just stick with the need to know, the stuff that's really important. I know that we're cramming a lot of information into each day of class, which is just the logistics of holidays and the way things are coming about. But we've got two things to cover. So if you need to pause the video, rewind and listen again, or if you need to ask questions in class, please don't hesitate to do so. So what we're talking about in general are functions. Okay, so a function basically describes how a dependent variable changes with respect to an independent variable. In other words, if this box is my function, I remember learning this clear back in elementary school. You take the independent variable and you put it in the box, and something mathematical happens. A bunch of adding and dividing and subtracting happens inside the box, and then out spits your dependent variable. That's your output. So this is kind of like your x that you plug in, and this is kind of like your y that you get out of the function. Now we call this one the dependent variable because it is dependent. It depends on what I put in for x. So if I have a function y equals 3x plus 4, I can plug in anything I want for x. It's independent because I can put in whatever I want. But my y value depends on what number I plug in for x. So my y is going to change depending on what I plug into x. So that makes x independent, and that makes y my dependent variable. Okay? So a lot of times we write these as ordered pairs. Again, if you're looking at this function like you have since middle school, and even before that probably, you've got your x and your y. This is your input. This is your output. This is your independent variable. This is your dependent variable. Okay, it's just your normal x and y ordered pair. So writing a function. For each situation, express the given function in words. So you're writing in a hot air balloon. As the balloon goes up, as it rises, the surrounding atmospheric pressure decreases. Okay, so the pressure changes depending on me going up. So I would say that the pressure decreases as my altitude increases. Right? As I go up, the pressure decreases. So as far as my function notation goes, pressure would be the dependent variable because the pressure depends on the altitude. So pressure would be my y value. Altitude would be my variable. That's my independent variable. Okay, so B, that's A. You're on a barge headed south down the Mississippi River. You notice that the width of the river changes as you travel south. So the width changes as I travel south. So that means that my width is dependent on the direction that I'm traveling. So my direction is my independent variable. Okay, because depending on the direction I go, my width is going to change. So direction is independent. The width would be the dependent. Okay. So I guess it wants us to write those as an ordered pair. So this first one, I would put pressure. Nope, I wouldn't. I would put altitude as my x and pressure as my y. For the second one, my direction would be my independent variable, and my width depends on my direction. So that would be my dependent variable. So representing functions, again, this is all stuff that you guys have seen multiple times over the last few years, but there's a few different ways that we can do it. I can give you a data table, which just says, oh, if my altitude is 7 or 10 or 25 or 1,000 or 6,000, then my pressure is equal to I'm just making up numbers, guys. This really is not significant. Then my pressure here would be 300, and my pressure here would be 280. And then we'll say 240 and 150 and 50. Okay, so that would be a table, right? Which, I mean, it gives you detailed information, but if I'm looking at a large number of altitudes, a large number of data, all of a sudden that gets really hard to read. Okay, tables are annoying, especially when there's a whole bunch of values that you're looking at. So one of the other ways that we use functions is we draw a picture or we do a graph of the function, which is we've kind of already talked about a little bit. If this is my function right here, I'm comparing the time, which is kind of like my x values. Depending on the time of day, my temperature changes. Okay, so the temperature depends on the time of day. The temperature does not control the time of day. The time of day controls the temperature. So down here would be my independent variable across the bottom, and going up the side is my y value or my dependent variable, because the time changes the temperature. All right, now domain and range, something we've been dealing with for years, but for whatever reason, it still causes a lot of heartache. Your domain is the range of values across the bottom. So for me, in this problem, my domain is going to be, if I look at my chart, it goes from 6 a.m. to 6 p.m. That would be my domain, 6 a.m. to 6 p.m. My range is all of my y values or my dependent values that respond. So my lowest y value is 50. My largest y value is 73. So the temperature goes from 50 to 73 as long as I'm going from 6 a.m. to 6 p.m. I would imagine that as I get past 6 p.m., my temperature might actually drop below 50. I don't know. Maybe we're in California and it doesn't. But so looking at these graphs, just a couple more representations. You see the temperature on the left and you see the time on the bottom. So as time goes on, this says time after 6 a.m. Oh, hours after 6 a.m. So 5 hours after 6 a.m., my temperature is right there. It's at a little bit over 60. 10 hours after 6 a.m., so at 4 p.m., my temperature is at like 68 degrees, all right? So that's your domain and your range. Again, things that we've seen a lot. The other way that we can represent functions is with a mathematical sentence, okay? We can use an equation or a formula to represent our function. So creating these functions. You can go ahead and pause the video and read through this creating and using graphs of functions. It kind of gives you some tips on the steps that you should go through to create a graph. I'm not going to take the time to read that to you, so pause real quick, read through it, and then come back when you're done. Okay, so example 3, it gives us a table, and it wants us to create a graph of this data. So I know I'm going to have something like this. And across the bottom, remember this needs to be across the bottom I need my independent variable. So it looks like this is our altitude and pressures all over again. So we said that the altitude was independent and the pressure depended on what altitude you were at. So across the bottom is going to be my altitude. Going up the top is going to be my pressure. So then I look at the values. Okay, my lowest altitude is 0. So that's good. This can be 0. And then it goes up to 30,000. So my highest is 30,000. And it looks like if I split this up and say, okay, so that's about 10,000 right there. That's about 20,000. But then it also gives me a 5,000 value, which is right there between 0 and 10. So I split up the bottom based on the values that it gives me. And then when I look at my dependent variable, when I look at the pressure goes from 10 up to 30. So I can mark 10 right here, and then let's say this is 20, and then this is 30. So now I chart it. At 0, At 0, my pressure, and let's use a different color here. At 0, my pressure is 30. So it's right there. At 5,000, my pressure is 25. At 10,000, my pressure is 22. So at 10,000, I'm going to go up here to about 22. At 20,000, I'm at 16. So 16, 15's right here. So at 20,000, I'm going to be a little bit higher than that one. And at 30,000, I'm at 10. Okay? So that kind of gives you a graphical representation of the data. And if I were to connect these, a lot of times we want to connect the points. If I were to connect these together, and sometimes I can get this to actually draw a curve for me, but not this time. So it looks like as I go to the right, as my pressure gets higher and higher, it kind of slows down, right? It changes really quick here in the early stages, and then it slows down a little bit. But the important things, your labels, pressure, altitude, your values on the side so that people know what numbers you're talking about, and then obviously the graph itself where you put your data. Okay, example 4, hours of daylight. The number of hours of daylight vary with the season. Use the following data for 40 degrees latitude to model the change in the number of daylight hours with time. So it looks like I'm going to have time go across the bottom, and I'm going to have hours of daylight as my dependent variable. So it says the number of hours, oh, look, we're talking about an entire year. So let's call this January, and then we've got February, March, April, May, June, July, August, September, October, November, December. Now, I'm not going to write every single one of these in here, but we'll write a couple so that we know what they're referring to. So that makes this one August, March, this one's April, this one's May. So that gives me some reference points. And then looking at the hours, I've got 14, 10, and 12. So not a lot of variation. My lowest is going to be 10, middle is going to be 12, and my high is going to be 14. I'm going to spread them out a little bit just so I can actually see what's happening on the graph. If I put them too close together, that's not going to look very good. So now when I actually model this, when I plot these points, it says that 14 hours is the summer solstice. So that's about June 21st. So if I go to June, we'll say mid-June right here. Mid-June, I'm up at 14 hours. That's my longest daylight day of hours. The number of hours is the smallest on the winter solstice, which is December 21st. So December, I'm only at 10 hours. And then it says that on the spring and the fall, so March 21st and September 21st, it's at about 12 hours. So March 21st is right about there. And what was the other one? September 21st. We're also right about there. So if I look at my graph from here to here, whoops, I didn't mean to erase. But that's not where I wanted it either. Come on, we want it right about here. Okay, so if I were to connect these, I go up and then I come down and then I'm back down here, which means coming into January, I'm actually coming from right here. So it's saying, looking at this model, what times of year does the number of daylight hours change the most gradually? So when does the time change the most gradual? And if I look, it's kind of hard looking at a diagram that you drew because your drawing could be awful. But basically, my diagram is going up, and then it peaks, and then it comes down, and then it peaks again. Okay. So if I'm looking at the slope, my slope is going to be highest right here and right here. That's where I'm going to be changing the most quickly. I'm going to be changing the least quickly, the least gradual down here, up here, and down here. So that means that in June, around the solstice, and in December around the solstice, that's when I'm changing the most gradually. Those are when I'm changing just a little bit at a time. But in March and in September, my daylight hours are changing really quickly. Those ones are changing quickly. All right? Okay, moving on. That gets us through 9A. So at this point, if you want to stop and do homework for 9A, you're welcome to. If you want to finish the video and get through 9B and get it done, and then just do them both when we're finished. But 9B is all about linear models, okay? Or in other words, our graphs are all going to be straight lines. That's what it means by linear models. So if I look at this diagram here, across the bottom I've got time. Going up I've got the depth of rain. So as time goes on, the depth of the rain gets deeper. And it looks like this is a pretty steady rainfall, okay? If it was raining like it does in St. George, where you get a whole bunch of rain and then a little bit, this might not be very accurate. But somewhere that it rains a lot, this is probably a pretty good representation. Okay? So now when I look at this diagram, there's a few things that stand out. First of all, if I start reading some of the information here, it talks about the slope. So remember, the slope is kind of our, if you go way back to, the rise over the run. Okay? How much do I go up for every amount that I go over? Okay, the rise goes on top, the run goes on the bottom. So in this case, from 2 to 3, that's 1 hour time. So I would put 1 hour on the bottom. And I go up 1 inch. So my slope would be 1 inch in 1 hour, which just simplifies to 1 inch per hour, right? So we're going to be using slope quite a bit. That rise over run is something that you're going to see as we go through this 9B unit. So here's a couple of different graphs, rain accumulation over time. And obviously we're looking at either different rainstorms or maybe different locations in the world. But this first one, if you notice that the graph is a lot more flat. It doesn't go up as quickly. And that's because if you look at the slope, for every hour, that's my run, that goes on the bottom. So in 1 hour, I only go up 1/2. I only go up 0.5. So that means my slope is only 1/2, whereas before, in this example, our slope was 1. So that smaller slope makes my graph flatter. It's not as steep. This second example, I go over in 1 hour, and I go up in that amount of time, I go up 1.5. So that's 1.5 over 1, which makes my slope 1.5 inches per hour. So it's a lot steeper because my slope is bigger, all right? And then even more so, this one on the far right, I go over 1 hour, so 1 goes on the bottom, and I go up 2, which means I have a slope of 2 over 1 or 2 inches per hour. So that slope, and that word drives me crazy, but it's one that just is so familiar to you. We have another name for that slope, and that is the rate of change, which is what I prefer. I prefer talking about the rate of change, okay? At what rate is the depth of the water changing? If we go back to these other graphs, at what rate are the hours of the day changing? At what rate is the pressure changing? If I say, at what slope is the pressure, what are you talking about? No, at what rate is the pressure changing, okay? So I prefer rate of change, but we've been using slope for years and years and years. Really, the good thing is the slope and the rate of change are exactly the same thing, okay? So it doesn't matter if you call it rate of change or slope. It still means how much does your y value change over how much does your x value change. So this would be y over x. Oh, actually, it's your change in y over your change in x. That's how you write change in, for those of you that are so excited for calculus next year, Elise. The other way that you learned this, you actually learned y1 minus y2 over x1 minus x2. So if you had 2 points, you could find the rate of change between those 2 points. So example 1, you hike a 3-mile trail and you start at an elevation of 8,000 feet. Along the way, the trail gains elevation at a constant rate of 650 feet per mile. The elevation along the trail can be viewed as a function of distance walked in miles. What's the domain of the elevation? From the given data, draw a graph. Okay, so let's draw a graph here. And it says that the elevation changes according to the miles that I walk. So we're going to put elevation over here and miles that I'm walking across the bottom. And it says it's a 3-mile trail. So I'm going to start at 0 miles, and then I'm going to go to 1 mile, and then 2 miles, and then 3 miles. And then my elevation, I start at 8,000 feet. So I'm going to put that right here. And a lot of times when we don't really know this distance, you'll see that it kind of breaks up that graph. It gives you 2 little lines right here to say that this part isn't to scale, but we're going to start at 8,000 feet. That's where I start when I hike. And then it says that I go up 650 feet every mile. So at 1 mile, I'm not at 8,000 anymore. Let's call this 9,000. Let's call this 10,000. And we should maybe add an 11,000 up here. So I'm going to go up 650 feet after 1 mile. So at the 1 mile mark here, now I'm up at 8,650, which is a little bit more than halfway between 8 and 9,000. And then a mile later, I'm up another 650 feet. So that's going to put me at about 9,300. And another hour later, now I'm at about 10,000 feet. Okay? So if I connect these, it's a line that goes from 8,000 up to, what did we decide? We were at 1950, so it ends at 9,950 is where I end. So every mile, I'm going to go up. Now, in the real world, well, we'll get to that in a minute. Sorry, domain first. The domain of the elevation. Remember, my domain goes across the bottom here. It's the independent variable. So my domain goes from 0 miles, where I start, to 3 miles where I end. It's only a 3-mile hike, so my domain better not go to 5 miles, otherwise you're walking off of something you're not supposed to. So my domain is just 0 to 3. My range, if I were to give you my range, I start at 8,000 feet, and I go up to 9,950 feet. That would be my range, because that is my dependent variable. Gives you your range. From the given data, draw a graph. We did that. Does this model seem realistic? In general, probably. If every mile that you hike, you might go up about 650 feet. But I would imagine that if we zoomed in really far, I would imagine that as you hiked, I would imagine that you did a lot of this. I would imagine that you went up and down, then the trail, maybe there was a hill, and then maybe the next hour, maybe there was a big hill or a big dip, but you're kind of going up and down, you're going flat. Maybe for a minute you don't even move at all. But when you zoom out, those little bit of ups and downs seem realistic, that in general, you're going up 650 feet. That doesn't mean you're going up exactly that amount or a fraction of that amount with every step. Or you could be in Wyoming, and the reason they built the railroad track through Wyoming and Nebraska is because it basically looks like this. It's really, really flat, and it has a very, very, very gentle slope. So this would be realistic, especially if you were hiking somewhere like that, where it was a gradual slope. Okay, a small store sells fresh pineapple based on the data. For pineapple prices between $2 and $5, the store owners created a model in which a linear function is used to describe the demand. So the number of pineapples sold per day that varies with the price. So the number of pineapples sold is going to vary the number sold is going to vary depending on the price. So the price is going to be my independent variable. At the bottom, that's going to be my price. The number sold is going to depend on the price. That's going to go up. And it says, for example, so we're just looking at prices between $2. So this is one. So here's $2, $3, $4, $5. Here's $5. It says at $2, there are 80 pineapples that sell. So if we go up here and say, all right, this is 80. So at $2, you sell 80 pineapples. It doesn't give us any more information. In fact, I probably should have copied that one down. Here's the rest of the information right here. At $5, you sell 50 pineapples. So let's go back and say, okay, at $5, if this is 80, here's 60 or 70, here's 60, here's 50. So at $5, you sell 50 pineapples. So this is a linear graph. And it wants to know, what is the rate of change for this function? So the slope, or the rate of change, remember, is the rise over the run. Now, if I look at my graph, my rise, I'm going from here to here. So I'm going to go over 1, 2, 3. So my run is going to be 3 on the bottom. But I'm going to go down 30. I'm going to go over 3 and I'm going to go down 30. So I need to be careful because my rate of change is negative 30 over 3. Okay, when you're calculating slope, if you go to the right, that's a positive number. If you go up, that's a positive number. But when you're calculating rate of change, if you go down, that's negative. If you go left, that's also negative. So right here, this is a down. This is going to the right. So I've got negative 30 over 30, which simplifies. Negative 30 over 3, not 30, is basically negative 10. So your slope, your rate of change, is negative 10. So that means for every price that I go up, every time I go up $1, I sell 10 less pineapples. I sell 10 less pineapples. Now, this doesn't talk about the values at those points, because right here, if I sell 80 pineapples at $2, that's $160. But if I sell 50 pineapples at $5, that's $250. So even though I don't sell as many, I sell them for more, but I actually make more, which you don't see all the time. Sometimes there's this balance where if you sell it for too much money, it goes way down. And that's where I bet if we zoomed out, I bet if we dropped this so that the price of a pineapple was $1, then you might not be able to have enough pineapples to sell them. And I bet if we went all the way up to where the price was $10, you might not sell very many pineapples, which means that's going to cut into your profit quite a bit. But at least from $2 to $5, this rate of change is pretty steady, all right? So, rate of change rule. And all this boils down to is we're manipulating the formula a little bit. This says that it allows us to calculate the change in our dependent variable from the change in the independent variable. So, my change in y is equal to my rate of change multiplied by the amount that I changed of my x, okay? Remember, the triangle means amount changed. So the amount of change in y is equal to the rate that I'm changing multiplied by the change in x. So use the linear demand function to predict the change in demand for pineapples if the price increases by $3. So I'm looking for the change in demand. So my demand is equal to the rate of change. Well, we said our rate of change was -3. Nope, it wasn't -3. Our rate of change was, bad math, Mr. Reed. Our rate of change was -10, right? Right here, -10. Our rate of change is -10. And I multiply that by my change in independent variable. Remember, that was money. This was the number sold. Nope, that wasn't the number sold. This was the number sold. So the change in demand is equal to -10 multiplied by the amount of money that I changed. And I changed by $3. So that means that my demand is going to change -30. So that means that I am going to decrease my sales by 30 pineapples. I'm going to sell 30 less pineapples than when I increase by $3. Okay, we can also go the other way around. You can find the dependent variable. And I guess we'll get into that another day. What it wants us to get into, and it's just more algebraic manipulation, but it wants us to talk about the general formula for a linear function. So the dependent variable is equal to your starting value plus your rate of change times the independent variable. This looks familiar, right? The dependent variable, y, is equal to your starting value, your initial value, plus the rate of change. I don't know, maybe we should call rate of change m, and our independent variable, x. This looks a lot like y equals mx plus b. That's because it is y equals mx plus b. X is your independent variable. Y is your dependent. M is your rate of change or your slope. And B is your starting point. Where did you start initially? Okay, but it's the same formula you've known forever. It's just written with the initial value in the front instead of the back. So the rain depth equation, use the function shown to write an equation that describes the rain depth at any time after the storm began. Okay, so if here is my graph. So y is going to equal, we're going to call this y and we're going to call this x. Actually, maybe we shouldn't. That would be too easy. Let's call this d our depth, and let's call this t for time. So my function, my dependent variable, d is a function of time. So I'm going to write d of t, or you can just write d, same thing. D of t equals, now I need my starting value, which is right here. When t is equal to 0, then my dependent variable is 0. Before it starts raining, there's no rain. Well, duh. Plus my rate of change. So if I go over 1 hour, I go up 1 inch. So I have 1 inch over 1 hour, which is just 1. So my rate of change is 1 multiplied by my dependent variable, t. So d equals 0 plus 1 times t, which is just 1t, which is just t. So my rain depth varies exactly with my time. So in 2 hours, I'm going to have 2 inches of water. In 3 hours, I'm going to have 3 inches of water. In 4 hours, I'm going to have 4 inches of water. That's an easy one to write. How about the price of pineapple? Write an equation for the linear demand function. So here is my x, or my independent. Here is my y, or my dependent. But let's again, rather than using X and Y, I'm going to erase that. Let's use, for demand, let's call that D. And for price of pineapples, we'll call that P. We can call it whatever we want. But my demand is equal to, it wants the initial value first. So when my independent is 0, my dependent is 100. That's where I start. Then I'm going to add my rate of change. Well, my rate of change, if you remember, my rate of change was -10. So -10 multiplied by my dependent variable, the price of the pineapple. So I'm going to put a P right there. So D of P equals 100 plus -10 times P. And I'm going to rewrite that to say 100, this plus minus right here, 100 minus 10P. So D of P equals 100 minus 10P, or just D equals 100 minus 10P is one way that you could write it, okay? There's lots of different ways. We could say that Y equals 100 minus 10X. We could say that if this is my X, then this is 100 minus 10X. We could write it as an ordered pair. I like this one. I like the function notation. We like to write it that way. I like to see it that way. Okay, homework 9B and 9A, if you haven't done it yet. Again, it's just a repeat of a lot of things that you've seen, maybe just written a little bit differently, like this general form. It doesn't want mx plus b. It wants basically, really, all this is saying is y equals b plus mx. Other than that, it's the same thing, okay? Good luck.